Okay, so today in the session, I will be recapping what we were building up last week, and basically today we will start discussing integrals of more interesting objects. So to recap, we were discussing how to iterate integrals, and I posted in the playlist the corrections for the notation and some comments on what it means to be composing those integrals. So right now I'm writing something like this: GL minus 1 until G1, and then here we can have some f of g, which is basically f of g will be part of the full Grassmann algebra, which we were denoting with span of all possible Grassmann words and over complex numbers. So in the end, what will come out is that if in this case f of g can be expressed as mu in the Boolean cube, so that's the notation for the session today, and f mu g of mu is basically what I mean by f of g. And by using linearity, you actually see that this is f of mu, and then so this we will define as integrating against g, f of g, and then g of well, the point is that the whole thing collapses, and then I will have the g of 1 word here, right? Okay, and then here f of 1. So that's something special about those Grassmann integrals. Basically, if I'm integrating against all of the generators, they will be removing Grassmann numbers as they go, but then sometimes they will meet something that they didn't see, and then it will be dropping to 0. So this entire summation over all the indices mu becomes just this number f and the index of the full word, and if we use consistent sorting, then this becomes f1. So that's quite an important thing, because now we will be interested in integrals of different expressions, and in particular, I want to define a function actually, and then we want to define a function xa to be just defined by this first of all formal series n factorial 1 over this, and then a to power n. Yeah, so that's the standard definition of this. But if a is in the Grassmann algebra, then first of all I wanted to show a computation. So maybe at some point, if we decide to make a little bit of an off topic, I would show a little bit about representation theory of Grassmann numbers and integrals. But Grassmann numbers we can basically represent as triangular matrices. So maybe choosing the upper triangular matrices, and in some way they will be nilpotent. So now we can make a simple calculation. So if I have a, which is some expression in GL, which is the Grassmann algebra generated by L Grassmann numbers, then a to power L plus 1 is equals to 0, no matter what it is. And that's a simple calculation. So maybe we do a proof sketch first of all. Let's say a is equals to g1. Then a squared is equals to 0 already. So in particular, 2 is smaller than L plus 1. Yeah, because I have at least one Grassmann number smaller or equal than. And now another question is, for example, A could be some summation, so G1 plus G2. Then A squared is G1 times G2 plus G2 G1. Yeah. And that one is already kind of 0, right? Because the anti-commutation. So depending how you do it, but if this wouldn't be 0, then I could still add a to power 3, and this would have to be 0, and that's sort of my point, which is basically called the pigeon hole principle. Yeah. So now, if we do the general case where we are computing so in general, a will be a function over mu in the cube, and I will have the coefficients a mu and g of mu. Yeah, and now if I start taking powers, a squared, I can again write it as a summation of mu, and then here some restricted summation of nu prime, and with some conditions on mu. So here we are summing up a mu, maybe a mu plus nu or something like this. There will be some coefficients, and here you can collect them again into some g of mu. But the point will be that basically the grading will be increasing. So what I mean by grading, so if I have a Majorana what? Sorry about the plane. G of mu. So my words are ordered like this, mu L. So now if I multiply G mu times G nu, then what do I need to do? I have G1 mu 1 until GL mu L, and then times G1 nu 1 until GL nu L. And the way to proceed it is basically to iterate through the entire G of nu string, and basically anti-commute until you come here, then you take the second, and anti-commute until you come to the second, and so on. And for this, to keep track of this, it's useful to define a function, which is in some way already, I'm not saying that it's a symplectic form, but I'm kind of saying it's a little bit like a symplectic scalar product. So G nu this, like this. We could sum over k strictly smaller than k prime, and then I take mu k and nu k prime. So we are basically summing over some sort of triangle. And so it's a double summation, and basically I'm claiming that this G mu factor allows you to keep track of the I would need to check it for next time whether this is exactly this one. We can also do the computation now, but then I can write this as a regular summation of two vectors in the integer space. So now I view mu nu as in z vectors in ZL. Yeah. So basically, it's putting the polynomials together. You will get some phase functions. So so this one I put a question mark because it depends on the sorting. I think the way I wrote it, it works for even L only. But anyway, you will have a plus minus 1 function here that depends on mu and nu. Basically, if I take G1, and if G1 is here, then I have to sum over mu L minus 1 until mu 2. And then I put them together, and suddenly I will have G1 to power mu 1 plus nu 1, right? So that way I can collect them. So so then weight here, which is some k from 1 until L of mu1, we could call the grading of G mu.
Mu
So,
k, right? The summoned.
Yeah. Thanks. Okay, so this is the grading of G of mu. We could define this, right? And we could also have the grading in Grassmann number k of G mu. This would be just mu k, right? And to give another example, so another example would be the grading of G mu plus nu is in this case mu plus nu. But the problem is that we are doing everything modulo 2 because they will start dropping down, right? So anytime if mu k, wait. So now I want to explain that this grading needs to be done modulo 2. So modulo 2, and the reason for this is that if there is some k such that mu k is equals to nu k, then I just take those two, put them together, and then I will have jk to power mu k times jk nu k. As soon as they meet, both equals 1, both present, then I have jk to power 2, which is 0. So our grading is sort of defined. So the grading in k has to be somehow defined modulo. Wait. So this one maybe we don't need to define modulo, but this one is the one that I need. So wait. Okay, I will add k, and then it will be fine. Because I need the one in a given Grassmann number. So here modulo 2 k in grading k here, yeah. Because okay, and now I can come back to this, and I was saying that basically we start multiplying them. So so let me go to a new place. So I have any expression in the Grassmann algebra mu g of mu, and now a squared is a summation nu a nu, and g mu g nu. And now if I would take this phase function that I didn't compute carefully now, this is more technical, so maybe not so important, but you kind of see the point that if I exchange the Grassmann numbers, then I get some plus minus factors, and whether I have them in or not, it depends only on mu and nu. So there's a plus minus function here. Yeah, and that's my multiplication here, but you kind of see that this grading in k has to increase or you drop to 0, right? But now if I take a power of al plus 1, then by the pigeonhole principle, I have to have some Grassmann number, because like this mu, I define that mu cannot be 0. Yeah. So unless you would have some other identity, but we don't have identity in our expression here. So yeah, so I will always have some g mu and g nu where both are non-zero, which means when I multiply them, they become non-zero only if they go to different places. So those mu nu strings cannot be overlapping, right? So actually, I could say that mu intersection with nu has to be non-zero, because otherwise they drop to zero. That was the argument previously. Yeah, but now if I will have L plus 1 powers, then I had L plus 1 polynomials. So this is a summation of polynomial mu1 until mu L plus 1. So L plus 1 multiplications. And I could also set up the notation here. So I remove all nus and I will add just numbering. So mu1 comma mu2, mu1 mu2 1 2, mu2 mu1 mu1 mu2 mu1 mu2. Okay, so now I have a multiplication of g mu1 mu2, sorry, until g mu, and the point is that this is L plus 1. So as long as all of them are non-trivial, then they drop out. Yeah. So so if I actually should write it here that mu should be non-zero. And then we should define what do we mean by g of 0 here. So actually g of 0 should be some identity symbol. And that would make sense to add this kind of identity symbol, because I want to define the x function in a second, right? And then I will need to 8 power 0. Okay, so I wanted to say that this is basically some sort of nilpotent algebra, and when you take too many powers, it will start dropping to 0 in general. Yeah, because if you think about them as triangular matrices, at some point it goes to 0. So basically here the length is sort of L, and if you put L plus 1, then it doesn't work. Then the pigeonhole principle will start applying, and you kind of start seeing it here, because this will be proportional to summation mu k, yeah, and k from 1 until L plus 1, yeah. And if all of them are non-zero, then there has to be at least one k where the number will be higher than 1, yeah, and then it will be 0. So that's the proof sketch, yeah. That's important because exponentials of expressions from this Grassmann algebra here are actually truncated series. So n from 0, and now at most until L, yeah. And then I have 1 over n factorial, and then a to power n. Okay. So example, a is equals to just one Grassmann number G1, then x of G1 is the identity plus G1, because this is G1 to power 0 plus G1 to power 1 plus G1 to power 2, and plus the zeros, yeah. Now I could continue this a little bit longer. So for example, what might be interesting is G1 plus G2. G1 plus G2, and just from the Grassmann property, we get identity G1 plus G2 plus G1 plus G2 squared, and you can finish it here, right? And then you can compute whether this one is 0 or not. Okay. Okay, there's another airplane, but I will just continue. So that's the important bit, that that those exponentials they are nicely truncated. Oh, it's still quite loud. So. Okay, and the most important, the most important exponential that we will be dealing with today will be an exponential of a quadratic form, where what I mean by this expression here is that I just sum over k prime from 1 until L, and then I have the matrix elements of k prime, and then I take the Grassmann number gk prime. Okay, so we want to look at this one, and what we will actually find is that that in this case it actually makes sense to consider L going to only even dimensions. To justify this is that basically it's a little bit unhandy. So okay, maybe I talk about this because that's sort of the point of going to those things. Okay, so I have, for example, GTMG, and the question is, what kind of conditions should I put on the matrix M? And what we should find is that it should be antisymmetric. So this is summation MK K prime GK prime K prime from 1 until L. Those indices are important because now I can restrict it to ordered indices, and then I will find that I have MK K prime, GK prime, and then plus M K prime K GK prime GK. Yeah, so this is basically equals to K prime MK K prime minus MK K prime K, and here I can already order it GK prime. Yeah, so if you take a matrix, so it can be any matrix C L by L, then creating a quadratic form is actually you can take the antisymmetric part of the matrix. That's something that a Grassmann quadratic form does. So there is a lot of redundancy because if I add, if I split the matrix M to the symmetric part plus antisymmetric part, then GTMG is actually equals to GTM antisymmetric part G, because the symmetric part will vanish. Yeah. So here for the symmetric part GTMS G, I will be summing K smaller than K prime, and the symmetric component of this is 0. So the antisymmetric component of a symmetric matrix is 0. So this is 0, and this becomes 0 as well. Yeah, so that's a calculation that we will be repeating because later we will be going to free fermions. So maybe Lucas will be doing those lectures. But then you can replace, for example, GKs by Majorana operators or creation or annihilation operators. And then you realize that you can actually restrict any matrix that you choose to the non-trivial component. Yeah. So so those matrices should be antisymmetric. Now, an antisymmetric matrix, and that will be useful, any matrix which is minus its transpose, then there exists Q such that Q I should say Q QT. Okay. this becomes k from 1 until L. This becomes 0 minus lambda k 0. But here I would be restricting this in this case to 2L by 2L. Okay. And the reason for this.
And what kind of matrix is Q?
So there exists Q in SO of 2L, such that this Q in SO of 2L. Okay, and I will give you a reason for that. It's basically consider the matrix A is equals to IM, then A is Hermitian, which means it has purely real eigenvalues. And what this form means is that M has purely imaginary eigenvalues. And those eigenvalues are plus minus lambda k. Okay. Now the problem is that if I have an in odd dimensions, this matrix M has a kernel. So there will be some lambda eigenvalue of M, which is such that lambda is equals to 0. Yeah, at least one will be 0, and then this QQ transformation, when you find this special Q, it will be k from 1 until L, 0 minus lambda k minus lambda k 0, and then you need to add sort of the 0 matrix, a one-dimensional matrix. You need to add this one row, and when you remove that 0 eigenvalue, you have an even matrix again, and it's quite similar. So we could discuss this a little bit later, but I think Lucas might be doing more geometrical pictures and talking about metaplectic representations and so on. Then it's kind of so later on you will have this, but for this the paper is Bloch Messiah from the 60s, I think. And they do it quite carefully for complex matrices, and that's the calculation I know. Another calculation that you can do is based on this A matrix. Let's say that I diagonalize A by U dagger, would be some diagonal matrix, yeah. Then Q you can take to be real of U, and then imaginary of U, and then transpose or not. You need to know the conventions. But basically, the trick is done by taking the real and imaginary parts of U. This is something you can do yourself for 2L by 2L. We can also do it in a separate session. Today I didn't prepare a quick discussion, but basically you just need to know that there exists such a matrix, how to work with this, and then to know which paper to cite. And that's really a paper that focuses on it. So it's very transparent there. It's more or less a linear algebra paper. Okay, so here we have this one. So I was discussing now with the quadratic forms, and I was discussing that we can take them to be antisymmetric, and then I wanted to motivate why I want to consider from now on L to be actually 2L. So I will be considering G, capital G, Grassmann algebras generated by an even set of generators. so that they always pair up, and I don't need to worry about this one block that is always 0. Yeah. So here I'm already correcting it, and from now on, m will be c to power 2l by 2l. Sorry, another thing.
Yeah, don't worry about. I hardly hear them.
Yeah,
I think
because
the
here is
noise
very loud.
cancellation is taking
Okay.
care of it.
Yeah, then it's working well. Okay, so basically, for practical reasons, for now, let's discuss those exponentials of like that. And one more thing that I wanted to add is that let's say I have a b in my Grassmann algebra, still general, but I define it by plus, which means I take the span of g of mu such that the full grading such that this one is even, and that one is a good restriction, because on so even polynomials in those Grassmann generators, they behave like numbers finally. So I kind of the point of those sessions is to kind of explore together in what way those are numbers, in what ways those are integrals. So here I can show you why. It's because x of a times x of b is x of a plus b. And the reason why is that basically for all a, b in the even part of the Grassmann algebra, we have a, b is b, a. So the BCH formula is kind of triggered. Yeah. And the way to do is to say, okay, let me take some monomial. I take two monomials in the even restriction of this Grassmann algebra, and now I multiply them together. G mu. Okay, I need to do it more explicitly. G1 mu1. Can I do it correctly? Mu L, and then G1 mu1 L mu L. And now the point is that if I would be moving through those even expressions, so let's say I want to move this one through, then I know that nu is 2n, like it's even, right? So if I would like to write G1 mu1 until GL minus 1, mu L minus 1, and then G of nu, I do it slowly, G nu 1 until GL minus 1 nu L minus 1, then I have GL nu L, and then I have GL mu L, because I moved it through. Okay, so what I used is GL commutator with G of nu. This one is 0. It's 0 because when I moved it through, I can say that they are equal because I made an even number of transpositions, and each transposition which was non-trivial costs a minus, but I made an even number of transpositions, so I get a plus. Yeah, and then I can iterate this. So basically they are meeting, and either this will be 0 if nu L is equals to mu L is equals to 1 or something else. But if they are non-trivial, you can just continue doing this, more or less. That's the idea. Okay. So because we are commuting, the exponential function works like this. So this is so A, B are numbers. Yeah, that's this one question. Okay, I think we are kind of a bit slow today, but we are explaining those details. And now the point is that I actually introduced what is needed to start making integrals of those functions. So wait, I wanted to say that. Okay, so we saw that the series truncates. The truncation I was doing by the pigeonhole principle. And then I was showing the first time when they start behaving like numbers. So I didn't discuss this general case for the commutators carefully, but you kind of see the idea for the quadratic form. That will be quite easy to see, I think. Yeah, and now I want to show, so series truncates, they start behaving like numbers, and now I will show you that they start behaving like for example, like Gaussian integrals. So we saw that they are behaving a little bit like numbers. So now let's see whether this behaves like a Gaussian integral. And I want to show that this is the Pfaffian of M. And I will introduce what is Pfaffian. So what this is. And we will find two ways of proving it. The first way of proving this is by symmetry. So first way by symmetry. Or actually, no. I will come to the symmetry if we will have time. Otherwise, I will do it next. The symmetry would be using this block Messiah form. Anyway, so now I'm taking this antisymmetric matrix on an even space. This is a transposition, and then 2L by 2L. And first of all, what we want to show is that that because this 2L is coming here, the first thing to notice, so there's a reduction of simplifications, and we are always using the Grassmann conditions. We need to show that this is GTM to power L. So notice this is 2L, and then the maximal power of GTL becomes L, yeah? So, okay. So how do we prove this? We have the exponential of GTMG is the summation from n equals 0 to, now the question where I should be truncating it. So I was saying before 2L plus 1, but now I'm taking a quadratic form. So actually we the truncation will be much earlier. GTMG to power n, yeah. And so what's happening? If I expand this, to say that this is some m n mu g of mu. So I'm taking all the products, I'm collecting all the coefficients, and then I will have g of mu, right? If this g of mu is not equals to g1, then I was saying it's somewhere here. I need to have the top element of the algebra present. So the integral against all of the Grassmann numbers is picking up the coefficient of all of the boxes landing there. Yeah. and they can combine in different ways, but ultimately they cannot basically. So we need to show that we can restrict this to L, and we need to show that the lower ones are incomplete. So I'm integrating against all of them, and this G mu is, this is just the Grassmann integration formula for more Grassmann generators, yeah, the iterated integral. And now the question is, which kind of power can produce, which N can produce G of 1, the full index, yeah? If N is too small, then you cannot produce it, right? So let's say I take G1 and G2, then the second power will give me G2 or G3, G4, and then I need to continue it. So this gives me the full index on the first one, and here is N equals 2. Then G5, G6 is N equals 3 and gives me on this on 6. So L equals 3, and then we continue this here until GL minus 1, G2L minus 1, G2L. So I needed L powers to do that. If I will use too few, then whatever pairs I have, either they will overlap and drop out, or they will be non-trivial, but they will give me something which is lower. So I need to have precisely N. Yeah. So in the exponential, you have the summation here until L. Okay. But if I'm integrating it, then the integral against all of the G's will be the delta, and it will choose only the full expression here. Yeah. So now what we the only thing that we need to study is GTM, G, the Lth power of this quadratic form. And what it is basically, so I'm summing over J1, J2, MJ1, comma J2, G1, GJ1, GJ2, okay? And now I need to take it to power L. So I do that. And I'm doing it by summing from J1 until J2L. Why? Because if I have L powers, then I need to double the indices. So I have M, J1, J2, all the way until M and J sub 2L minus 1, comma 2L, GJ1, GJ2, dot, until G2L. That's the Lth power, just multiplied out. Now the next problem is that I need to find G1. So how do I find it? Is that I take any J and GJ1 until GJL, and I have some okay. So another thing is that now I'm okay. Sorry, I went a little bit too fast, because what we need to realize is that none of those indices, J1 from 1 until 2L, none of those indices is allowed to repeat, because if, for example, J1 is equals to 5 and J15 is also equals to 5, then basically inside of this Grassmann expression, I move them close together. At some point, I will have basically G5 to power 5, yeah? I will find somewhere plus minus G5 to power 2, and then the rest of them, but this is 0, yeah? So they cannot repeat, which means that I actually can sum over permutations, sigma in the symmetric group to L, and then I will have M of sigma 2k minus 1, comma, sigma of 2k. And here I have just a regular product from k equals 1 until L. Yeah, just writing those dots as products. And basically sigma will be a permutation, and it will give me all the possible assignments of j1 until j2L, so that this sum is non-zero. Yeah, it will give me all the summands. So that's the coefficient here. And here we have j sigma of 1 until j sigma of 2L. And the last thing is, how do we reorder it? But this is exactly what the sign of a permutation does. So if I had 1, 2 until 2L, and here I had j1 until j2L, then I can write this as 1 until 2L in this permutation kind of array. And here I have sigma 2L. So out of the ordered string, to generate the sigma string, I need to make some transpositions. And now the parity of those transpositions is kept by the signum function of this transposition sigma nu. Then I have the product from k equals 1 until L. And then this notation with 2k minus 1, comma, sigma 2k. And here, finally, I will find from G1 until G2L, right? And this I can pull out because this doesn't depend anymore on sigma. That's the point, right? So if you will not mind that I will erase this stuff here, we come to the definition of a Pfaffian and Pfaffian of M, okay, and G of 1. Yeah, if I would be integrating that thing, I would just get the Pfaffian. Okay, so we arrived at this formula. So the integral over all possible powers, so we take all possible powers here, but first of all, we saw that we need to truncate them until L, not to L plus 1, until L. 2L plus 1 is just saying they are always truncated if this is a series. But for a quadratic form, it's just L. That's the truncation. Then another thing is that if I'm integrating against all of them, then the only non-trivial integral is if you have all of them inside. Otherwise, it will drop something which is not 0. It will be 0. Okay? Which means we need to ask which kind of powers can produce G1. The lower powers don't produce, which means they drop due to integration. And then here we were computing that power. And when we computed this power, we actually used the antisymmetry of those Grassmann numbers to actually count the number of swaps that we need to do to order them. But they are essentially, all of them are plus minus the full Grassmann expression, the top of the algebra. Yeah, and they are counting only the plus minus signs, and this is exactly the signum function. And the matrix function of a matrix which takes all the entries with the signum function here is called the Pfaffian. End of story. Yeah. So now we are taking a while, but I want to show you that suddenly we can start using Grassmann integrals to start proving theorems. So I can write M Q lambda Q. Now I can define a G tilde set of vectors to be defined K prime from 1 until 2L because we have an even number of those. K prime, GK prime. So this is what I'm calling Q acting on G. And now I will redefine it so that, no, where do I want this one? Yeah. Yeah, I want it here, right? And that's the kth element of this one. So if I have a quadratic form written like this, I can write this as a quadratic form written like this, G. But this I can write as a quadratic form for those tilde generators. And I have lambda, G. Now what lambda was a direct sum from k equals 1 until L. So those blocks are 2 by 2, which means I'm dropping the 2L. 0 minus lambda k, 0, so like this. Which means that this quadratic form expressed in those tilde generators is actually a simpler form, and that will be popping up later for quadratic Gaussian Hamiltonians. So when we go to Gaussian states of fermions, this will be popping out. But now I will have that actually the only non-trivial elements is 2k minus 1, 2k, g2k minus 1, g2k. And plus lambda 2k, comma, 2k minus 1, g2k minus 1. Okay, but because I have this notation, so here you kind of see that I have basically a block diagonal form like this, and those 2k minus 1 and 2k variables are the ones that are, so k is selecting the block. So that's the first block, this is the second block, this is the kth block. So k here is selecting the block, and inside of the block I have the off diagonals. So I'm selecting the off diagonals inside of those blocks. This is actually useful to do it like more slowly, because this is appearing all the time. So now I can write lambda k, g2k minus 1, g2k. Okay. So now I can write the exponential of g to m g as the exponential of summation over the blocks, lambda k inside of the block. I might have a plus minus there, but the plus minus is just a convention there. Like this, but we know that they commute.
The G's on the right side should be the, yeah, okay.
Yeah, thank you. Yeah. So, but this is a product. It's so now I'm writing even a product symbol because all of them are commuting. And we can check that exp of lambda k g to k minus 1 g to k is actually the identity symbol plus lambda k g 2k minus 1 g 2k and nothing else. So this integral becomes much more simpler. Lambda plus lambda k g 2k minus 1 g2k. Okay, so I will call it theorem. Pfaffian of the matrix M, yeah, is the product of those block eigenvalues, lambda k. That's the first theorem we get directly from Grassmann numbers. And for the proof, I need to show that gk exp of gtmg is the same if I switch to g tilde, but this is the tq, so determinant of q basically for each of the integrals, right? If I want to switch, and then I'm just integrating this dtgmg, but then to get the full one, so to get the full one, you need to take the products, yeah. So suddenly it becomes much simpler. So I know that this is Pfaffian of M. And after I switch to G tilde, so the determinant of Q is equals to 1 because of the Bloch-Messiah theorem. And this number, we can show that this is multiplication of lambda k, because I need to get G of 1, yeah? And to get G of 1, I need to, in each product, I need to select lambda k and those two. Because if I select 1 once, I will not get the full one. That's the only way to get the full one. Select all of the lambda k's. So that's the top of the product, yeah? And we are getting this, so that's not a Pfaffian, that's supposed to be a proof. And that's supposed to be a theorem, because I'm not really doing it carefully and I'm discussing all the assumptions, right? But the idea is that suddenly Grassmann integrals and changes of variables here are revealing something to us which is not so obvious. Another thing that we can try to prove from the integrals is that if I transform a matrix Qt, that this will be the determinant of Q and then the Pfaffian of M, yeah? Which is kind of working, because if I would, because I'm getting on the other side Pfaffian of lambda, actually, yeah? So this product here, this is actually Pfaffian of lambda. So suddenly those integrals are telling us something about transformations here. And that's a difference. Pfaffian and determinants, they have a large symmetry group, which is the SO symmetry group, and the this permanent function, which doesn't have those signs, it has a tiny symmetry group. So bosonic Gaussian states are somehow more difficult to compute. And here it's much easier, because we have Pfaffians and determinants. And this also tells you one more fact. This is easy to compute, because you take the spectrum. You take the spectrum of IM, or the antisymmetric part of this, and then take the full product of the spectrum is the Pfaffian of M, yeah? So it gives you a quick, efficient algorithm to compute the Pfaffian, yeah? And the idea to, I mean, people have developed those things in linear algebra, but you could arrive at this just by setting up anti-commutation relations, then have a good idea for this Berezin integral, for the Grassmann integral. Then we developed all the kind of transformation rules of Grassmann integrals, basically saying it's linear maps and they have to transform this way. Then you consider a natural object an exponential function of a quadratic form, and you learn new ideas about what Pfaffians are doing. No, if you would just go to the Wikipedia page of Pfaffians, you will see, for example, the Pfaffian is equals to the full product of the spectrum of the antisymmetric part of IM. And like, how do you get this? Or you will find this formula on Wikipedia as well, with this determinant. And we are getting this basically to in a way that that Grassmann numbers are like a counting device, and then we are just dropping things. And the first time we saw that the Grassmann numbers are acting like a counting device is when I was showing that the antisymmetrization is dropping here. This is the first time where multiplying something together with Grassmann numbers shows you that you somehow are doing transformations on different objects. So now another thing that we did, this is just to summarize, sorry that I'm taking a bit longer today. To summarize is that if you take the integral, you're selecting the identity coefficient, and suddenly you are putting together things with Grassmann numbers, taking different powers and blah, blah, blah. And you get a nonlinear function because this is a highly nonlinear function of M because it's the product of all the spectrum. So Grassmann numbers are transforming coefficient matrices in a quite nice way. Yeah. And they are also showing you relations between those things. So it's not so obvious just, okay, let me show as a final thing the definition of Pfaffian. I will highlight. So, wrong color. So the definition of the Pfaffian is we are summing over all permutations, taking the signs and taking this product here, and that's the definition of Pfaffian. You look at this, and you wouldn't say that this is a product of the eigenvalues of IM, right? Because, for example, if this wouldn't be here, it's a permanent, and that's basically boson sampling. So suddenly there's a very strong interplay of what the sign is doing and how you do it and so on. If I would be summing here over K from 1 to L, and here I would have L, and here I have like K, then the same thing would give me the determinant. Yeah. So we can talk later about some other tricks to relate Pfaffians and determinants and so on. Yeah, but that's sort of my moral of the story, is that suddenly you see those Pfaffians appearing from the integrations, but you also learn about relations between the integrals. And that's my point, that we can use those Grassmann integrals to derive different relations between different numbers and so on. Right? So, yeah. Good. I finish here.